Really excited about this podcast. Was able to work with Jack Lilly and Paul Rudd and Caelan to talk about test specimens, especially the tensile specimens, and what are the challenges we face in trying to get good properties. I mean, the tensile test is supposed to qualify that the steel that we've made really will meet the expectations of the customer, but isn't a guarantee of what the properties are in the casting. But even making a test block, getting the test bars and then doing the test on the test bars can be challenging. So this was a really interesting discussion. I hope you enjoyed. If you have any questions, please follow up with me. If there are other details or questions you have, please let me know. I thought our last session went really well, talking about test bars and test materials. And I want to talk about the test specimens themselves this time, and then go back and talk about test block design and test blocks. Thank you, Jack and Paul and Caelan, for joining me. And what I want to do first is I want to go through some slides because I think a lot of that is really fundamentally important to our discussion. This is something that is really fundamentally not understood, and that is that elongation and reduction in area and strength are artifacts of the normal testing specimen. If you change the geometry of the specimen, you get different results. And there are two different results you get. So this is just fascinating. You can see that, that if I have the straight bar, I get the normal curve where I have yield strength down around 40 KSI, and then I get almost a 60 KSI for my ultimate strength. And I have elongation that's 35%. But if I just taper it down to that center, what happens is I get a dramatic reduction in the elongation and reduction in area. And the strength, both the yield strength and ultimate strength, go up. And as I make this angle sharper and sharper all the way down to just a saw cut, I end up with the highest ultimate strength, the highest yield strength, and the smallest elongation. So when you have a flawed test bar, you would expect to get yield strengths that are the same as the non-flawed test bar, but you'd expect to see a dramatic reduction in elongation. And this is exactly what we saw in a lot of our work. So this is an ordinary alloyed steel. You can see that this is a 505 test bar. So the sound material has 100 KSI. If I drill a 1/4-inch hole halfway through the specimen, so I've removed a huge amount of material, the yield strength's only fallen by 20 KSI. And you can see when I have a smaller amount, especially if I have the flaws in the test bar instead of drilled holes in the test bar, you can see that I have almost no effect on yield strength. But as soon as I get a hole, my elongation drops dramatically. And this is the fundamental reason. We talked last time about the fact that the test bar really was supposed to be a test of how good the steel was, not how good the bar was. And so if you had a bar, even today in ASTM, and you can see a flaw in the fracture surface, to qualify the heat, you can throw that bar away and test another bar, because you're not interested in, can I make a good test bar? You're really interested in whether or not the steel meets the properties you would expect. So this, I think, is really sort of a critical set of concepts for people. And this is the different kinds of materials. This graph came from Daryl Sosey. Now, Daryl Sosey works for Dr. Mitchell when the large OEMs were trying to move from make and break every new design to computer designing the components. And so this goes back to the 1970s. This is 50 years ago. They were trying to grapple with, can I use finite element analysis instead of making and breaking every component? So Paul, at least you and I remember when Caterpillar when they designed a new structure, every component they designed, they had a big Butler building. They took it out there and put hydraulic cylinders on it and broke it and made sure it would actually survive. And so Ralph Stevens, who did our research report 94A and B, which are available free online to anyone on fatigue and fracture toughness, he looked at both fatigue and fracture toughness. Fatigue, there are two different regimes for fatigue. If you are a plastic material like this, then what they found was the life-limiting feature was initiating the fatigue crack. And so they developed strain control fatigue crack initiation. If, on the other hand, you had a brittle material, a really high-strength, low ductility material, what you had to do is pretend anything on the surface or anything in the microstructure could act like a crack. And the life was determined by how rapidly the crack grew. Stosey's graph here is brilliant. This is the yield strength in English units, so this is pounds per square inch. This y-axis is the fracture toughness in KSI per square root inch. And so if you take the fracture toughness divided by the yield strength and square that number, that's how big of a plastic zone you have in front of the crack. That's supposed to be a measure of how ductile or how tough the material is. And the reason Stosey likes to do it in English units is since this divided by that squared is the plastic zone, a line with a slope of 1 when you square it is 1 inch. You've got a 1 inch plastic zone. So if you're close to this line, then you need 3 inches thick to get plane strain, and you need a ½ inch flaw size to even begin to worry about fracture toughness. And so this is really brilliant. So he tells that the carbon steel materials are here, the alloy steel materials are here, and when I really want high strength material, the Mar-aging steels or the things you used to make, Paul, for ground engaging tools, I'm way out here where I have 50 KSI sort of as a minimum fracture toughness, and I may have a yield strength that's 150 or 200. And if I'm up in the 200 range, then I've got less than a ¼ inch critical flaw size. But what this really means is that for most of our materials, they're really not fracture sensitive. They're really primarily plastically driven. And you can see this because Stosey told us, by the way, as a steel guy, I have to point out aluminum is here. It's not very tough and is not very strong. And titanium is here. It's also not very strong or very tough, but both of these are lighter than steel. So people like to use them to save weight, but that's the only reason to use them. And so the funny part is in steel, we think if you have less than 10% elongation that you have no ductility. In aluminum and titanium, if you can get over 10%, you've died and gone to heaven. I mean, it's just unbelievable. Anyway, these samples here, I could actually do this elongation versus yield strength sort of measurement, and you can see that you get two different kinds of behavior. If I'm in that ductile steel that tears, then the only effect I get out of having massive holes, ¼ inch holes, is the elongation drops dramatically. The strength changes almost not at all. You can see that the strength is virtually the same. You get a little bit of reduction when you have a huge hole in it, but even relatively big holes, you're right here, okay? Even ordinary features in the casting. So these are drilled round holes that are more severe than the porosity we find in the microstructure. So one of the questions design engineers often have is, yeah, a drilled hole isn't bad, but maybe that thing in the porosity acts like a crack. And so Stosey actually had us drill the holes to show that drilled holes were at least as bad as the porosity we have. So they're not cracks. They just are features that reduce the cross section. When you're talking about ductile materials, when you go to the high strength materials, it's kind of stuff used to make for ground engaging tools, then not only do you get a reduction in ductility, and you don't have much ductility to begin with, but you almost immediately start to get fractures so that it cracks instead of tearing. And so you can see that you get both low ductility and you rapidly lose strength. And then the ordinary materials we have, the primary thing is that they act more like the ductile material than the high strength material. You get some erosion of strength, but until you get to very large holes, you have minimal impact on strength, but you get a tremendous impact in ductility. So that's really a fundamental challenge. So there's about 3 things when I have test specimens that don't meet one of the properties that I recognize, which is the redundancy in it. If I meet the ultimate strength and not the yield strength, I'm not particularly worried, because the ultimate strength is the best measure I have. And the yield strength can be affected by all kinds of other things, including the way I make the measurement or the surface finish. And I know, Paul, you'll want to come back and talk about that, but those are really fundamental, or alignment of the machine. So yield strength and ultimate strength are redundant. Elongation and reduction in area are redundant. So if one of those is correct, I'm pretty confident that the material has the properties I want. But there are other ways of looking at this stuff. And so one of the things that people have been doing lately is to use the yield strength tensile strength ratio instead of elongation or reduction in area. And it has the great benefit, number one, that it actually means something in design. So in design, if I have a small section, like in the test bar, a reduced section, it doesn't matter if I get to yield first, as long as the ultimate strength is high enough compared to the yield strength that it'll yield somewhere else before I break in that reduced section. So yield strength, ultimate strength ratio can actually mean something in design. The other real benefit of it, and this is not expected, when I put holes in, the yield strength, ultimate tensile strength ratio doesn't change very much. I mean, when you look at this graph, you can see that the holey specimens are actually on the same line as the sound specimens. You have to get to very large holes before you begin to see any effect of getting towards this line, which is theoretically the safe line. And so to me, one of the things I do when I have test bars that don't meet the properties is to look at the yield strength tensile strength ratio. And if it's where it's supposed to be, then I'm confident that that bar had a hole in it. And so this is really, I think, one of the more useful things to look at. The other thing is Charlie proposed a quality index, and that was used by the aluminum people to look at test specimens and see whether or not they had enough porosity to affect the properties. And so I did 2 things. One is I took all of the ASME boiler code and plotted the elongation ultimate tensile strength requirements in green. And then I got a bunch of data sets, and these are mill products, properties from the data set. And you can see that even though we didn't know it when we set all those specification limits, they are at the lower bound, and they're generally around 280 is the lower bound. It turns out that 280 is a good number for castings too. So these orange are the ASTM A148 grades. So I take the minimum elongation required and the minimum ultimate tensile strength required, and when I plot that, I actually end up on the line that's really the minimum properties I'd expect from all the Quinston temper data I have. So this is about 10,000 data points, and it includes 4,300 materials, 4,100 materials, and 8,600 materials. So this is really powerful. And I know, Jack, you're going to ask me, did I do the holy thing? And I did do the holy thing. This is the holy thing. And you can see that if in the quality index, if I miss the bottom of the quality index, but I meet the yield strength tensile strength ratio, I am absolutely confident that that specimen had a hole in it. It's really dramatic. These are the sound specimens. Some of these obviously had some limitation in their ductility, and these are all the ones with holes. So you can see almost immediately with holes that you see a real reduction in that quality index, which makes sense because that's exactly what this says. All you're seeing is no change in the ultimate tensile strength. You're just seeing a dramatic reduction in the elongation. And that's all this is saying, is that your quality index goes down dramatically because you get almost no change in the ultimate tensile strength, but your ductility drops dramatically. You can see that, as you can imagine, over the last 10 years, I've increasingly gotten into discussions between customers and foundry suppliers on specimens that fail to meet the minimum specification requirements, both in the test block area, which we'll talk about next time, but also when they take a specimen out of a casting. And of course, as we talked about last time, taking a specimen out of a casting is not a commercial requirement. So it's not defective if it fails to meet the specification requirement. And it could have an impact on how it performs in design. But unless you know the load of the failure or the load of the problem you have, you don't know whether you met the design intent or not.
Well, can we go back to that very first slide?
This slide, yes.
So you were talking about the best design for a test bar would be one that has no taper and no notch. Okay. But ASTM allows some taper in the test bar so that you assure that it breaks in the middle between your two points. So I guess my question is, how much taper can I have before I get in trouble?
You know, Paul, that is a great question. As I was talking about that this morning, I remembered, since you are a high strength guy, when I was at Southern Research Institute, when you're talking about limited ductility materials with high strength, you've got a couple of things you've got to worry about. One is the alignment of the grips from top to bottom. Sure. Even a minor amount, a few thousandths of an inch misalignment will really cause the ductility to be much lower because you get a little bit of bending stress on it. And of course, because it's really looking for the weakest part in that cross section, if you don't taper it, it's going to break outside of the gauge, right, probably next to the grip. And you don't want it to break next to the grip. So I was thinking today, when I was talking about it early on, that I bet the fact that we always taper it means that the ductilities we measurement are uncharacteristically low of the material.
That's why I'm asking. That's why I asked the question.
It's a great question. And I was thinking, it seemed to me that we were talking a few thousandths of an inch.
Yep.
Taper, right? It wasn't very much at all. In fact, if I remember correctly, the machine shops thought as long as you could measure a taper and had the smallest diameter in the middle, that's where it was going to break.
Right, that's true. But my question is, even with the ASTM allowance, is that causing a problem? You know, when you're talking about elongations, whether you've got a 10 or an 11 or a 12, you know, is that little bit of taper in there going to cause a problem with elongation?
Oh, that's a great question. And one of the things I failed to put up here that I could look for in a minute, but I routinely have posted the ASTM reproducibility. And the reproducibility of elongation is greater than 1%. And that's not 1% of the number you measure, it's 1% elongation.
Yeah.
It's almost 1.5% elongation. 1.26, I think, is the right number. So when you start looking at that, one of the things when somebody's concerned about elongation, if I miss it by less than 2%, I don't think it's meaningful. I don't think it's a meaningful difference. So I think from a physics and metallurgy standpoint, you're correct. It affects it. And if I was just below the limit, that could be enough to have kicked me over the edge on the one hand. On the other hand, if I was only 1% elongation below, if the customer didn't give me a pass on that, I think I'd try and find a new customer because I don't really want to work with people who are that incompetent.
I don't think you're going to make it in sales.
I think you're right there, Paul.
Or in customer relations, customers can't find employees who can make that decision.
Yeah. Oh, absolutely. Absolutely. That's a real problem these days, is that customers can't find it. I use this as an example, by the way, when I'm talking to designers, that elongation isn't really a mechanical property, and that having a reduced cross-section doesn't mean that you're going to fail below the yield strength. It actually means that if you have a reduced cross-section in a complex geometry and it failed, it probably exceeded the yield strength you use for design. And it certainly, if it's a failure, exceeded the ultimate strength you use for design. That is why in the Navy, when you're welding together HSLA 115, you use an undermatched weld rod, and it works fine because that undermatched weld rod is actually like diagram F. You've got a very narrow band of material with higher ductility and lower strength, right, and you can't do it. One of the ways I've always explained this is to say, the problem here is you can't satisfy Poisson's ratio, and you can't find a favorable failure path in shear. So I can't find a shear path to fail on, and I have to put a lot more energy in to begin dislocation and failure because I can't satisfy Poisson's ratio. I may want to start to pull apart, but to pull apart, I have to get smaller, and I can't get smaller.
Yeah. Raymond, I can go through some of the things I've found in the last year working on test bars.
Oh, I'd love it. I'd love it.
That I found to be really important that I see in a lot of foundries. And they're all seem to be having problems with failing test bars. But here's some of the things that I found. First of all, people not Burnelling the test bar before they break it. And if you don't have the right Burnell on that test bar, you might as well not test it and you not machine it for sure. And what happens, one of the things that happen is the actual taking of the Burnell measurement. One of the things I see is that they don't necessarily grind below the decarb layer.
Okay.
And when they do, they leave this dished out area with the impression in the middle of it, which means that the scope can't sit down on the impression. It's held off, especially if the stand on the scope is large. And a lot of the Burnell scopes have a 1-inch diameter base that they use. And that will mean that if you don't grind absolutely flat, that the scope will sit up and give you a false hard reading because the scope is sitting off of the impression. Okay, I see this time after time after time. So the solution there is to have a Burnell pad that you grind. So it's roughly, say, 100 thousandths high that you grind, and that makes sure you're below the decarb layer, number one. And number two, hopefully it means that the Burnell scope will sit flat on the indentation. And the way you check that, of course, you can take a credit card and put it on the grind and see whether there's a curve there or whether it's indeed flat like you really want it. Okay, and that's a huge thing because I find test bars that aren't anywhere near the right hardness, and yet they go ahead and machine them and break them and they fail. And guess what? There's a reason that they fail. And if, like I say, if they don't meet the hardness area, then you might as well not bother to machine it. Just go ahead and reheat treat or grab another bar or whatever.
Yeah, so that's great. That's great advice, Paul. I think that's right, because I've done a good bit of work looking at the correlation between Burnell and ultimate. And if you're working in English units, if you divide Burnell by 2, you're pretty close to the ultimate tensile strength. It's really straightforward, but when you look at the repeatability of Brunel, it's poorer than even the measurement of yield strength. So you get a lot of variability in Brunel, but what you're saying is absolutely true. If I'm way below the hardness level that I need for that grade, there's no reason to machine and break that bar. Agreed.
Yeah, absolutely. Yeah. So that's why I'm suggesting, I think, for foundries is that management types or technical director type guys get out there and audit that procedure and see whether it's really doing what they expect that it is doing.
Now, are you skeptical? I mean, historically, we've said you have to use Brunel rather than Rockwell because you don't get enough volume of test with Rockwell and you do with Brunel, but you probably have enough experience. What's your experience of the use of Rockwell as an additive to or as a supplement for Brunel? Is that really problematic?
Yeah, it's problematic. I don't like Rockwell at all for castings.
Okay.
And it's for various reasons, but the Brunel test, if it's done properly, I think it really shows you what the hardness is. I don't think there's any question about that. Or the Rockwell is too small an impression, and these micro hardness people, you might as well forget that. That doesn't mean much of anything.
Good.
But anyway, so that's one of the things. But you
So,
need to
Paul,
audit. Yeah.
how many Brunel tests? Is it just one, or how many do you need to estimate before you machine and test that bar?
That's a good question. And I think just one done properly, one done to a procedure, and one that's been audited, and calibrated and things like that. And you're absolutely right. If you have a Brunel that's like 300, you can expect a tensile somewhere around 150,000 psi. It's a linear deal. I mean, there's no mistaking it. You better have the hardness or you're not going to meet the strength level.
Right.
That's all there is to it. So that's one of the things I see that's wrong. And another thing I see all the time is the actual machining of the test bar and leaving scars when it's being turned. In other words, if you don't have a good RMS on the test bar, any flaw that you have is going to cause degradation, especially of the elongation reduction area, like we've been talking about. So.
Yep. And that is absolutely key. And especially from your background, when I'm talking about carbon steels, it doesn't matter very much. But as soon as I start talking about your high strength, high hardness materials, it's absolutely critical. And like I said, the alignment, you have to have self-aligning grips and have alignment on your tensile test too. Because either surface finish flaws on your test bar or misalignment will give you low elongation. No question.
Yep. So, and then of course, then we get into heat treating, and bars should be absolutely clean before they're quenched to make sure they get the very best quench. The water temperature needs to be controlled to make sure that we get as much, and I'm talking here again about high strength steels. Sure. We need to get as much martensite, in fact, 100% martensite anytime that we can. And that means that the test bars need to be in a position where they'll get good water flow, to break up the barrier of vapor that's around the test bars and so on. So, and then for smaller test bars, smaller test blocks, they need to get into the quench fast. But on the other hand, the big guys like the 4-inch test bars probably don't have that, don't need that kind of urgency. But anyway, obviously heat treating is a big part of this. And the precision of your tempering furnaces then becomes mandatory, no doubt about it.
Yeah, and of course, that's one of the things I think we'll have at least one, maybe two more sessions, because one, I want to talk about solidification of the test blocks, because that's poorly understood, because people think if they get a sound test block by radiography and by solidification modeling, that's all they have to do. And there, as you and I both know, there's lots of tricks there that are not obvious in terms of solidification behavior and heat treatment. So, Jack, you've done a lot of the high alloy stuff. How much of this stuff applies to your austenitic materials? You don't even have to tensile test a lot of times.
I think it applies a lot, especially in I'd say lower strength materials, but lower strength, lower ductility materials.
Okay.
You know, the petrochem, the heat resistant alloys.
Okay.
A lot of those have mechanical property requirements at room temperature that don't necessarily really make sense from a fitness for service because they don't operate at room temperature for very, very long.
Sure.
But are nonetheless barriers or obstacles that need to be dealt with. So some of the things Paul talked about, surface preparation, even to the point of not only leaving flaws, but are you work hardening the surface, and is that affecting either your yield strength measurement or your elongation measurement because you're altering the microstructure because you're too aggressive.
How do you do that? I mean, if I'm a foundry that doesn't ordinarily make it, but I got an induction furnace and I get an order for CF8 and I make the casting and they want a tensile property, how in the world do I machine a test bar without work hardening the surface in 18.8?
Well, and 18.8 is probably not the grade that I'm worried about. Like I said, I was thinking more of the heat resistant alloys, where there's less ductility and so forth. But you're probably, I think 18.8s are pretty forgiving.
Okay. So the heat resistant alloys, what do I have to do in terms of turning that bar not to work hard on the surface? What's the trick there?
It's in preparation. We have some double prep where there's machining and grinding, surface grinding, to get the best surfaces possible with the minimum impact on properties.
Okay. Yeah. I had never thought about it until you mentioned it in these heat resistant alloys, which are all austenitic, and they're going to work harden if you do traditional machining, especially if you don't know what you're doing and making light cuts.
Well, at the risk of being blasphemous, if you venture onto the dark side of bronze and copper-based alloys, they run into that stuff all the time. And they'll do things like rouging the gauge length. They'll machine it and then they'll use some jeweler's rouge to polish up and get a better surface to eliminate flaws and for the same kind of reasons.
Yeah.
Oh, that's good. Yeah. I was interested when I was up at your place last week and saw all the copper stuff you do about the whole notion of maybe Steel Founders Society creating a copper division.
Well, I've been working that issue with Dave Powlett, and I've been lobbying in the background because I think it's fertile ground, and I think there's a need for it both within the society and within the broader technical community, because I can't think of a copper reference. I mean, I know there's NIFs, but they're not very technical. And while there's several university centers on the steel side, Colorado Mines, Missouri, Carnegie Mellon, there's more out there. I can't think of one copper center out there.
Oh, there's no question there's not one in my mind. I've had members like Willie down at Fimex because they do brasses and bronzes, and they had a kid that wanted to do graduate work in copper. So I asked the professors at the universities we work with, who's really the copper expert? And I got zero response. And so if you ask me a copper question right now, I called Tommy Horton down at Lempe Reich, who doesn't do that anymore, but has a really rich background in copper, brass, and bronze stuff. And the little bit I know says that there's not much. You have to read just about everything that's ever been printed just to begin to get your arms around the challenges. And the one that always strikes me as a real problem is the oxygen content in the copper alloys as an alloying element that you generally don't see anything written about, you're not aware of, but as soon as you talk to people who deal with copper, brasses, and bronze, they're well aware of the need to control oxygen content. Really...
Well, there are grades. Oxygen-free high conductivity copper is a grade.
Yes.
So it's
absolutely. So,
So
Caelan, you made bars. Did you guys do tensile tests? Did you have any of these problems, or are they as perfect as everybody thinks they are? You just roll it and all those problems go away.
Um, we absolutely tensile test for long products. I'll say we don't tend to see as much of the triaxiality problem just because we're not making complex parts at the end of the day.
Yeah.
But I'm sure they're running into the same sorts of problems of I've got low ductility and I don't know why. Uh, now to a certain extent, we don't have as big a porosity because we close it when we hot work it. So that's not necessarily, we're not as concerned, I'll say, about holes in our test bars.
Yeah, yeah. The one thing I know about mill products, and I have a couple of slides on it, is if you go from doing longitudinal tests to doing transverse, especially short transverse testing, you can see just the same problems we have with porosity with the inclusions, because you're basically making them into pancakes. And when you're looking either at the long transverse or longitudinal direction, you see the edge of the pancake, but when you look through the section, you see the pancake itself, and that really hits you pretty hard.
So usually, at least what I've seen in long products, you do tensile tests longitudinally. Some customers might specify a transverse, but when you think about it, most of the bars are 4 inches and less in diameter, so it's
Yep.
difficult to get a transverse. Um, for premium products, you tend to see longitudinal Sharpies, but sometimes also transverse, and transverse is where you'd expect to see the worst performance. That's not unexpected for any of this. It varies a lot from customer to customer and what they require, the size of material you're making, as to your orientations you tend to test. But it's a well-known phenomena in the rock products that the orientation of your test will have a massive impact on the results you see.
That's an interesting question that I wanted to ask both Paul and Jack, and Paul may know more, but maybe not. On Sharpie V-notch, I haven't been able to do anything like I do on tensile bars in terms of the yield strength, tensile strength ratio, and that sort of thing. But I have been able to take, for high toughness material, the HY material, I could actually have a referee for toughness with their dynamic tear test and look at which Sharpie value gives you the best indication of toughness as measured by the dynamic tear. I actually correlated 4 different measures of CVN. You got average, then you got the high, medium, and low value. And it turned out that average was good, but better than average was the maximum value you got. And the worst measure in correlation was the lowest value you got. So one of the things I've talked to Navy about, and I'm interested in maybe even doing some project work on, is would we do better to bust 5 specimens and take the top 2 as a measure of toughness, rather than bust 3 and have to make sure that the lowest one is 2/3 of the minimum value, which if it's not a good specimen, I don't know why I care what the value is, but maybe you have some other experiences.
One thing I have experienced is in Sharpies, if you break 3 specimens, 2 of them are the same value and 1 is radically different. There's something wrong with the test, not the material. Okay, yeah. So that's one thing that I've seen. Another thing I do remember, going way back, and it may not apply today, but what I do remember is when we started doing work with K1C, that there was a pretty good correlation between room temperature Sharpie V-notch and K1C.
Yes.
And I don't know whether that's useful at this point or not, but that's one thing that I can see as far as evaluating materials is to maybe do that. Rather, the K1C test is expensive and hard, whereas the Sharpie V-notch at room temperature is relatively.
For this graph with fracture toughness, one of the reasons you don't have to do much in K1C is that if I just use 50 KSI per square root inch, I'm probably okay. I probably don't need to do a number. And this is one of the odd things that we don't do very much lately, is we think in terms of science. And so we worry about whether I'm here or here. And it doesn't make any difference because the variability of the test is bigger than that.
Oh,
So as
sure.
an engineer, if I look at this, if I use 50 for my number, then that means that a quarter of an inch is 50 divided by 100, which is half, and then I square it and I get a quarter of an inch. So that means that for any of the ordinary steels where the yield strength is around 100, then a quarter of an inch is going to be the critical flaw size. And that's what the boiler code has. So when you start looking at it from an engineering standpoint, you can see that. These are the materials like mar-aging steels and the specialty alloys like the cobalt-based stuff. And that's the real goal of most of this high performance steel, is trying to get further out here and further up here. So a lot of the research we're doing with DoD funding is trying to move these up here.
Yeah. Well, one thing I can say is that, if you get to the point where you're going to use fracture toughness data, you've got a lot of teaching to do to engineers. Yes. Because it's been my feelings, and what I've seen is, we did some work on one particular part. We were worried about critical flaw size, and so we did some K1C testing and found out, lo and behold, the critical flaw size was 3/4 of an inch.
Oh, yeah.
Yeah, so you can say that, but when you say that to an engineer, he just shakes his head. And, he just basically says, we're not going to have a 3/4 inch crack in this area,
I agree with you completely. I've been on projects like that where it's a carbon steel, so I have the fracture toughness from Stevens' work on it at minus 40 degrees. And it's like 100 KSI per square root inch. So the critical flaw size is an inch or an inch and a half. And you go, yeah, this isn't very meaningful. I think we do want to do the test block next time, and I'll try and get some solidification stuff together for the test block. I especially want to talk to Charlie about looking at the lines of symmetry and the changes in cooling rate in normal test blocks, wedge blocks, to show that there are certain regions that's problematic. And we actually have data for high strength materials as a function of how far away they are from the bottom. And of course, they drop dramatically as you get towards the center line. So I think that could be useful. But maybe after we talk about heat treatment, I'll try and put together something where we can talk about toughness and Sharpie V-notch, because there is at least one new thing in that field called a master curve. And the master curve says that if I know where the null ductility temperature is, I know what the fracture toughness is for all thicknesses and all temperatures. And so that old work that you were talking about, Paul, we actually put together something to estimate the null ductility temperature, because that was a big thing for Polini.
Well, if we're still talking about test bars, there's one thing I can throw in. When you're talking about the Sharpies and you're talking about toughness, the preparation and the quality of the notch obviously is paramount.
Yes.
And one of the things, there are several things that you can do. One of them is you have a tolerance, for example, for the radius at the very bottom of the notch. You can make a visual comparator that you can use at low magnification to find out whether your notch indeed falls within the window of the envelope of that radius. That's pretty critical. Another thing is to do low power magnification to find out whether you've got any scars, especially in the bottom of the notch. Scars that might be caused by a broach that has a broken tooth. It might have a piece of steel attached to one of the teeth and it drags as it goes through the specimen. Regardless of that, you need to occasionally take a look at these notches and see how smooth they are. If they're not smooth enough, one of the things you could do is you could polish them, and if you polish the notch, you'll pick up another 2 to 5 foot-pounds of energy. So, that tells you how critical the preparation of these Sharpies are. And it's something sometimes we take for granted. Some people broach, some people grind. I don't know that one's better than the other, but I do know that the importance of the notch is absolutely paramount for these.
It is, and of course, it's not clear how characteristic Sharpie is of the part as a whole, because you're sampling such a small volume of material. You're really talking about something that's a millimeter thick, that's 8 millimeters by 10 millimeters, and the microstructure features are on the order of a millimeter in diameter. So it's really, unfortunately, a test that the specimen is too small to be meaningful to the material. And I think that's why the high value is probably the most characteristic.
Unfortunately, it's the gold standard.
Absolutely.
No doubt about it. And it's just so popular with engineers. There's nothing I don't think we're going to do there other than just improve our own practices.
I agree completely. And for most design engineers, this has been surprising when I tell them that elongation, reduction in area, and CVN are historical legacy measures of the reproducibility of the material, but really have almost no meaning in terms of the design itself. Almost every designer I talk to that's knowledgeable will agree to that, but I'll find some folks who just vociferously disagree because they put a minimum elongation on their drawing, and you go, where do you stick that number in when you calculate the design? How do you use that number for anything?
Yeah.
So, Caelan, what have we forgotten to talk about?
So Paul mentioned earlier different size samples. How important is that? I mean, the standard tensile is a 505, and they're all supposed to be equivalent. Does that matter? Between 505, 357, 252, etc.
Well, some of the really high strength materials, you can't break a 505 with a standard testing machine. So you have to go to a substandard bar, and then you are really talking with some tricky stuff, like 1/4-inch diameter bars. If there's anything in the bar, it's trashed. So yeah, the size of the bar is critical, no doubt about it. Yeah. Yeah, there's certain, the very few tensile machines can break a 505 at the 300 KSI strength level. There's very few that can do that. That's 550, 600 Bernal, obviously. It's way up there.
I'm going to probably interject some more blasphemy, but a big part of on the petrochem side are integral test specimens, not from test bars. And because of that, in the small size of the walls of the tubes, there's a lot of subsized bars in that business, either 1/4-inch or a lot of 160 bars, to yield routine tensile properties. It's happening all the time, including creep testing. They try not to go that small, but creep tests as well, because that's what you can harvest from the wall of the actual tube.
Wow. Yeah, that's interesting. I'll have to remember to grab some stuff on integral test bars. Vic B. Hall, who Paul knew from Tabasco, used to say that a prolongation on a thick section test casting would tell you the properties of the casting had you not attached it to the casting, which I always thought was a great line. So anyway, that's good. This has been a good session. Any last comment?
You started off mentioning that the purpose of the test bar was to prove out the quality of the heat and not the quality of the test bar. But I think we need to remember is we all have to live with the quality of the test bar. And I find it's important to educate people on the shop floor as to how important that casting is. They all know how important the casting is because that's what you're going to ship to the customer. They don't all realize that a lot of the properties and information that's going to release that casting and let you invoice are coming off that test bar. And a lot of times they're treated like the poor stepchildren in the organization, and they shouldn't be. Okay. So it's important to train people about that and inform them so they understand how important they are and how they should be treated in terms of pouring practice, in terms of cleanliness and not getting slag and things like in the pour, and observing pour temperatures, observing good molding practices in the mold shop. It's not just the test bar; it's an important casting.
Yeah, I was witnessed one foundry I was in. They were having test bar failures, and they had switched hot topping, and that's all it took. You know,
Wow.
they had started having shrinkage near the surface of where they were machining the test bars, and of course, then there was segregation and all kinds of nastiness.
Sure, sure.
You're absolutely right, Jack. It's really all this stuff's really critical for. Yeah.
Oh, sure, sure. In the Navy, the test block has to see every thermal treatment. So you pour 2 test blocks. And so test blocks become a significant cost of the entire product. It's not trivial in any sense. So that's a great observation, Jack. Thanks.
Well, just adding on that thought, it gets really costly there because they got to follow through all the processes. So if you need to make enough test blocks so that you have enough representative section size thickness all the way through to the end, so that if you take an early test and you have to go reheat treat, you've got enough left over or an extra test block that's seen cycles so that you're representing the whole load, because you could get to the end and not have enough to test and you're screwed.
Want to thank Caelan and Jack and Paul for joining me on this podcast. I thought it was really useful to really explore how do we test specimens, what's the difference between testing high-strength specimens and ordinary steels, and how do we do it well so that we get the properties that really reflect the capability of the steel that we make. Hope you enjoyed it. If you have other questions, other ideas, please let me know. Appreciate your time and your attention. Thank you.